Take two. So hello, welcome to another day of physics. General idea today is I'm going to talk about the exam you have on Friday. Quick announcement about that. So today is the April 5th. Your exam is April 9th. So the question is, what the hell with April 7th? I'm just going to warn you now. Next class, Wednesday, is going to be an open review session. I'm going to come with a pretty much minimal level of preparation, and it's just going to be questions. People are going to tell me what type of thing they want to see, and I will solve whatever type of problem people want to see. If no one says anything, I just say, oh, never mind, and end the class. But basically, a big open session where I can cover whatever anyone wants. But that's Wednesday. So yeah, prepare ahead of time what you want. Bring me problems. What I want to talk about is today. What I'm going to do is I'm going to go through last semester's exam. As I go through it, I'll give other tips and tricks. I'll tell you how I graded again and that type of stuff. Setup of the exam, it's on Vanco Hall. It's going to look the same as last time, full of problems. You're going to go in, you're going to do the problems on paper, take a photo, upload it. That's the same general idea. Any questions about the exam in general before I do this? Okay, so the first problem will be conservation of energy. And conservation of energy has a lot of parts because it's going to be based off initial energy equals final energy. You're going to know you're going to want that. But energy is a sum of kinetic and potential. Well, kinetic energy has linear kinetic and rotational kinetic, and gravitational potential and spring potential. There are 4 different terms for energy, and you will not need always all of them. Sometimes I might do stuff with rolling. If I do stuff with rolling, you're looking at things like on the homework, Samus rolling down a hill, in class, a hoop and a disc rolling down a hill, and in the example problems, Donkey Kong's barrel rolling down a hill. But last time, and that might show up, even though it's chapter 8, that might show up on problem 1. Well, for last time, I did not involve rolling, and I did this problem from Smash Brothers, which you might recognize because it was on the homework this semester. It was new to the homework this semester. And in it, I say, the character Min Min from Ohms is recently added to Super Smash Bros. Min Min Ohms are large springs with a spring constant of that. And you know what? Let's start writing right on it. Which she uses to punch and fling away her opponents. Min Min pushes her spring arm against Steve, who is not moving, compressing at 1.2 meters, as shown in figure A. Steve has a mass. Assuming she has only the spring to launch Steve, how fast is he moving when it is no longer compressed? And after he falls 2 meters, how fast is he going? There's nothing rolling here. There's nothing spinning in a circle. And since there's nothing spinning in a circle, I'm not going to use this 1/2 I omega squared term. That's only for rotational. If you're doing with something rolling, then you're going to need it. And as I said, your exam might involve rolling, it might not. But this doesn't involve rolling, so I do not need it. Likewise, if I don't have springs, you won't require this guy. But I got springs here, so I got to include it. Now, in general, what I'm going to do is I'm going to say I have 3 spots, A, B, and C. And what I know is that my energy at A equals my energy at B equals my energy at C. That right there was 5 points. And in general, the energy at each spot is going to be equal to linear kinetic plus gravitational plus spring. And what I'm going to do is I'm going to write an equation for the energy at each of these spots. See, I'm going to do this by going and defining things about each spot. And I can say, okay, at A, I say, Min Min pushes a spring against Steve, who is not moving. So at A, my velocity is 0. At A, the spring is compressed in an amount x of A. And he's changing height. So here I'm just going to say my height is 0. I'm going to say my height is 0 just because, I don't know, he's standing on the ground. It seems like a good spot for 0. I'll do this for all 3 cases. I will figure out what these terms are. And so I'll say at B, well, Assumes you only the spring to launch Steve. How fast is Steve moving? I don't know what the velocity of B is. I'm looking for it. But I do know the spring is no longer compressed. And he's still at the same height. At C, we want to find his velocity. We'll go blue. So at C, we want to find his velocity. The spring is still not doing anything. If the spring's not doing anything, we don't have to include it. But now he's fallen 2 meters. Now he went down 2 meters. So I'm going to make this a negative 2m to represent him going down. And what I'm going to do is I'm going to plug those numbers into this equation and say EA equals, well, this was 0. So mg, well, y was 0 also. 1/2 k xa squared. At B, y and x were also 0. So those terms cancel out. And at C, well, literally what I'm doing is I'm just taking this first purple energy line and I'm just plugging in the values, canceling out zeros. Any questions though? So this has 2 parts. What is VB and what is VC? Oh, and side note, since I like to show how I grade things, oh, I can't do it in red this time. +4, +4, +4, +4. 1 for each term. Now, if I want to find this VB, I know everything in A. So I'll just say EA equals EB. Or 1/2 k xa squared equals 1/2 mvb squared. I can multiply both sides by 2, divide both sides by m, and then square root. I don't think I wrote down his mass, but it's in there, 81.6 kilograms. Any questions on A? For B, I say, what's this velocity? And I'll just say that EA equals, instead of EB, I'll set it equal to EC. Or 1/2 k xa squared equals 1/2 mvc squared plus mgyc. I'll subtract this mgyc from both sides. Multiply everything by 2. Divide everything by m. And then square root. Am I still on the board? I'm still on the board. Note that I'm putting that y as negative because I defined it as negative on the screen. And I'm out of space, so I'm just going to put in a box right here. That's the general idea. The first problem will be conservation of energy. When I do a conservation of energy problem, it will, without a doubt, definitely, you will need this piece and this piece. And you will probably need one of the two for the other two pieces. I've sometimes you need neither. It'll be one of the two or neither. I won't involve both. Though I haven't in mind for a good problem with both, but maybe I'll put it on the homework sometime. And big idea is that initial energy equals final energy. That's what conservation of energy is all about. Just make an equation for the energy at each spot, set them equal, and solve. Any questions there? If you want something slightly different to practice, and once again, I'm going to do problems on Wednesday at request. But if you want something slightly different to practice, look at things rolling down ramps. If I do a rolling one, or there's a pulley in a bucket that's going to be on the homework. That's an old exam problem, actually, back when I didn't make them interesting. Or look at like me on a pogo stick, or Sonic on a thing, or Mario on a thing going straight up and down. Those are old exam problems too. Okay. The second problem will be conservation of energy. This will be one. Oh, I didn't show the point breakdown there. Sorry, I forgot. This is usually one of the easiest problems and the easiest one to get full credit. The problem with conservation of energy is there's less partial credit. Oh, and since I didn't show the ending points, it was 2 points for each final answer. Was the last 2 points though. Because there's so few steps, there's usually very little partial credit. All conservation of energy equation problems though are based off two things. Two equations, and there's two equations for most everything. Initial momentum equals final momentum, where momentum equals mv. That is how you solve any conservation of momentum problem. Just writing those is 5 points each. 10 points just for knowing that that's going to be the equations. And that's always going to be the equations. Now, I can change it up a little bit. For conservation of momentum, I could go left, right, or up, down. Here it's up, down. I also could do things bouncing off, being inelastic or elastic. Or I could do things sticking together, like they're completely inelastic. We've seen both on the homework and in class. For completely inelastic, you can look at Spider-Man sticking onto a car in the example problems done in the notes, or on the exam problem day. And on the homework, there's Luigi throwing a shell, but there's another one. I honestly don't remember what it was. But this is bouncing off each other. And it says Spider-Man is in yet another fight with the villain, the Vulture. The Vulture flies straight downwards at 3.52 meters per second. Okay, so we have the velocity of Vulture initial. He's flying straight downwards at 3.52 meters per second. To attack Spider-Man, Spider-Man attaches a web to the Vulture and launches himself directly upwards. Right before they collide, Spider-Man is moving at 6.32 meters per second upwards. After they collide, the Vulture is moving at 1.85 meters per second upwards. So the velocity of Vulture final, he's going up now, is 1.85 meters per second. And I say, given the mass of Spider-Man and the mass of Vulture, what's the velocity of Spider-Man final? Okay. What I wrote so far is not correct. There was a mistake here. Anyone know what's wrong with it? Take that as a no. Velocity is a vector. You need to keep track of the direction. In a standard coordinate system, we say the positive x is to the right, and the positive y is to the up. To the up. Yay, words. If you look at this problem, I show the Vulture is initially going downward. If the Vulture is initially going downward, I cannot say the Vulture's initial velocity is 3.52. I have to say it's negative 3.52. It's negative because of the fact it is down. Just putting that negative sign, by the way, was 3 points. But now I can solve for this. What I'll say, once again, is initial momentum equals final momentum. And what I'll do is I'll add up each piece. The mass of Spider-Man, the velocity of Spider-Man initial, plus the mass of Vulture, the velocity of Vulture initial. That'll equal the momentum final. The mass of Spider-Man, the velocity of Spider-Man final, plus the mass of Vulture, the velocity of Vulture final. My goal is to get the Spider-Man piece. And let me look at where I gave points for. So I'm going to subtract this right here from both sides. And then I'll divide both sides by Spider-Man's mass. Side note, I did give 5 points for this right here, just because there was so little points on it. And I can plug in. And that'll give me 0.738 meters per second. 5 points. Now, if I look at my points here, I got 20 right here plus the other 3 on my screen. So I had 25 points and I only gave 23 points total. The reason why is I didn't answer the entire question. And when I put this on the exam last semester, a vast majority of people didn't fully answer the question. Because I say, at what velocity, magnitude, and direction? I want you to actually write the direction. So I got a positive value. Anytime you get a positive value, as we said earlier, that is up. So his velocity is 0.738 meters per second upwards. Now, changes I could make on the exam, as I said, I might have them stick together. Spider-Man catches the Vulture and clings on to him. I could do side to side. If I do side to side, right is positive, left is negative. That's kind of all I can change. Questions? Okay. The last 2 problems on this exam are going to cover chapter 7 and 8. And these could be the ones that cause the most headache. Because like the first problem is like it will be conservation of energy. The second one, it will be conservation of momentum. But these will be some combination of all of this plus maybe this guy if I feel like it. There's a lot of material that's going to be mixed together in different ways. So I'm going to give some pretty big hints here about this. And the first one is I have a lot, this is a lot of equations. And I don't have time to do them over and over again. So what you can do is you can kind of break the equations into groups. The relationship between linear and rotational kinematics, centripetal acceleration, torque, angular momentum, and energy. Now, energy might show up in question 1. If it shows up in question 1, you might not have to worry about it again. But here's the idea. This 1, 2, 3, 4, 5, 6 topics. These 6 topics, I'm going to want to try to kind of hit on them all. With this, once again, this first one, or this guy here, being a maybe. I would definitely these 5 though will get hit on. And so what it is you can kind of check them off as you go. If you see a topic covered, you probably don't need to worry about it much again. And let's keep that in mind when we go through these. But that's my big hint here. Is I group it like that when doing the problem. Maybe you want to group it like that and say, hey, this part uses torque. I probably don't need torque again. I'm not going to hit the same topic twice usually. The problem I started with last time said, in the movie Kill Bill, the character Gogo Yubari fights with a meteor hammer, which is a 5.21 kilogram bladed metal sphere at the end of a chain. Let's assume she's spinning the hammer in a vertical spin, as shown below, with a rate of motion of 0.881 meters. So, am I good? I'm good. So a mass of 5.21 kilograms being spun with a radius of 0.881 meters. If she spins at a rate of 86 revolutions per minute, okay, that's an angular velocity, and I'm saying 86 revolutions per minute. Anytime you see anything in revolutions or revolutions per minute, you need to convert. I don't give this conversion because I assume you know how many 6 seconds are in a minute. If you don't, I'm impressed you can tell time. But I want you to make sure you know how many radians are in a revolution. To do this conversion, I'm going to go and cancel out my revolutions to get radians, where one revolution is 2 pi radians. And I'm going to convert my minutes to seconds, where 1 minute is 60 seconds. And so basically, after some things cancel out, revolutions cancel, minutes cancel, it's the equivalent of 86 times 2 pi divided by 60, which doing that math is 9.0059 rads per second. For the record, 2 points for that conversion, which is low for conversion for me. So if she spins at a rate of 86 revolutions per minute, what is the tension of the chain at the lowest point? Tension. If I'm solving for a tension, tension is a force. Anytime I'm solving for a tension or forces, that's F equals ma. And if I'm doing F equals ma, that means free body diagram. That means free body diagram and force equations. And so, yeah, I can look into this. So, at the lowest point, what forces are acting on this weight? I'll ask you guys, what forces are acting on it? No one? Okay, guess not. The force is acting on it. The first one's gravity, because there's always gravity. Well, gravity will pull it straight down. That's just what gravity does. It always pulls down. The other one is going to be tension, but the tension is going to be along the string. So the tension is going to pull it up. Note, this would not be the same if I looked at the highest point. If I looked at the highest point, gravity would be down and tension would be down. But that is my free body diagram at that point, which +1, +1 for each of those vectors. See, what I can do with that is I can say F equals ma, up minus down. That means tension minus mg equals ma. But this is moving in a circle. And if you're spinning in a circle, your acceleration is centripetal acceleration. And centripetal acceleration always points to the middle of the circle. So in this case, it points up. So I have a positive value. Now, A of C, I can either say A of C is omega squared all or v squared over all. But in this one, I know omega. So let's use the omega version. And I'll just say T minus mg equals m omega squared all. And by adding mg to both sides, I'll get that T equals m omega squared all plus mg, or 5.21 kilograms times 9.0059 squared times 0.881 plus 5.21 kilograms times 9.81 meters per second squared. When centripetal acceleration shows up, it's not going to say, oh, this is the centripetal acceleration problem. It's going to be solving a force. But if I'm solving a force on these problems, yeah, do F equals ma, make your free body diagram, and just remember that there's a centripetal acceleration. Now at this point, I just did centripetal acceleration. So I'm going to cross that off my list. That's covered. Let's see what else I ask. I say, GoGo then lets out more chain, changing the radius to 1.1 meters. What would changing the radius? We're going from a radius, and let's switch up colors. Original radius of R1 equals 0.881 meters to a new radius, R2, of 1.1 meters. If she does not apply any new torques, what is the new angular velocity? I have a changing radius causing a change in angular velocity. That as she spins it, it goes slower because it's getting longer. That's angular momentum. That's all based off the idea that initial angular momentum equals final angular momentum, where angular momentum equals I omega. Because anytime you see something changing in radius or changing in mass and therefore changing speed, that will be angular momentum. And so I'll just say I1 omega 1 equals I2 omega 2. Well, I, as written there, is MR squared. MR1 squared omega 1 plus equals MR squared O2 squared omega 2. This green pen doesn't work very well. There we go. Now the mass is the same. It's not changing. So I can cancel out my m's. And I can say omega 2 is R1 squared omega 1 over R2 squared, or 0.881 meters squared times 9.0059 over 1.1 meters squared. And let's check. 5, 10, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 25 points. So that works. Now for this, we just did angular momentum. So let's block that guy off and say that's now been covered. Any questions about this problem? Okay. Now, before I go to the next problem, I can, oh shit, undo that. Before I go to this next problem, I can look at it and I can tell you what I need on this next problem. I can say I need the relationship between, and let me drive this home. There you go. I'm going to need something from this box, something from this box, and something from this box. I know that without doing the problem because that's what's left. It's going to involve torques, it's going to involve kinematics, and it's going to involve the relationship between linear and angular. Because that's what I haven't covered yet. Once again, problems 3 and 4, they're not related problems, but they are in material. Whatever I cover in 3 won't show up again in 4, and vice versa for the most part. There's some minor things that can, like the conversion between range of evolutions. And so let's look at problem 4. Now, problem 4, some of problem 4 was actually on the homework for you guys. I added it to the homework. And it's about Cloud swinging the Buster Sword. I have the link to the GIF here that I attached to the exam, but you've seen this GIF in your homework. And it says, do I have a Cloud? No, I don't have a Cloud. I have a Sephiroth action figure, but not a Cloud. I was going to grab the Buster Sword and start spinning it. It says, the protagonist Cloud spins his sword, known as the Buster Sword, upon achieving victory. The Busto sword is 1.86 meters long and has a mass of 47 kilograms. Okay, so we have, make some space, a length. Oh, I don't want to use pink so I can tell easily when I do the point breakdown. It has a length not to be mixed up with angular momentum. Different L. I acknowledge that's an issue, but it is what it is. And a mass of 47 kilograms. Pretty heavy. Cloud spins the sword 4 revolutions in 1.68 seconds. See, if it goes around 4 revolutions, that's the angle it goes through. It just says it goes through 4 revolutions. But anytime you're given something in revolutions, convert it. 1 revolution is 2 pi radians. And so the angle is 8 pi radians, which I could do that math. 8 pi radians is just 25.1327 radians. It does that in 1.68 seconds. Not going to lie, this involved me watching the GIF over and over again, using a stopwatch, timing it, and just counting. I have an issue. Assuming a constant angular acceleration and the sword starts at rest. What is the angular acceleration during that spin? Okay, I wrote down a lot of bits here, but anytime you see angle or time on these problems, if you see a theta or you see a t, that will always be kinematics. Kinematics are the only problems this chapter with theta and t. Or chapter 7 and 8. Which seems weird. You think theta would show up more in rotational problems because, angle it rotates through, but it only shows up in kinematics, and same with time. So I know this has to be kinematics because I know theta and t. And so I play my matching game. Now I didn't write down theta naught, but theta naught is 0 because theta naught is always 0. And I'll look at what I know. What doesn't pop up here, theta naught, theta, omega naught, t. What doesn't pop up here is omega. And the first equation and the last equation both have omega in it. So I have to use the other one. I should probably start showing points. There was 3 points for this conversion, 4 points for that equation. Theta naught is 0 though, and omega naught is 0. So this simplifies the theta equals 1/2 alpha t squared. I can multiply both sides by 2 and divide both sides by t squared. And so alpha will be 2 times 25.1327 radians over 1.68 seconds squared, which is 17.8 radians per second squared. Oh shit. Here I'm going saying I never cover the same thing twice, and I did heal. That is very unlike me. I then say, at the end of the first spins, what's its angular velocity? This is unlike me, because I actually am doing the same equations twice. I'm doing kinematics a second time. I normally don't do that. I did heal. But if you want to find the angular velocity in the spin photons, omega equals omega naught plus alpha t. Omega naught was 0, so omega is just alpha t. And so it's 17.8 radians per second squared times the time. 1.68 seconds. So something that happened last semester is I actually made a mistake when I wrote the exam and I didn't notice it, which was problem B was supposed to be asking for the linear velocity, and then I accidentally put in the angular velocity instead. And I was good at, like, the problem was supposed to be what is its linear velocity, so that you had to use these, but I accidentally wrote angular. And in my original copy of the solutions, it actually had that extra step going in, but because the wording was wrong, I changed it back. This one did not have a link between rotational and linear. That was just because I messed up. Trust me, I keep saying these boxes will have one of each thing. That will be the case for you guys. It just didn't last semester because of my mistake. But that covers this material. And as I said, it should have covered this material if I hadn't messed up. I kept grading it and I'm just like, everyone's doing angular, not linear. And then I went back and reread the problem, like, oh, I wrote angular. Great. So it should have covered that. So for now, I'm going to say let's pretend it did, because to get my point across I'm about to make. I've checked this semester already. The only thing I haven't covered yet then is torque, energy, and kind of the stuff I put in yellow. As I said, energy might not always show up, but torque will. So without reading part C, it's probably going to use torque. It's probably going to use torque because that is what is left. And I want to try to cover all of this material. And so I can look at it and say, how he spins the blade is to apply a ridiculously large force at a distance of 0.045 meters from the pivot point. If this force is perpendicular to the sword, what is the force needed to cause the angular acceleration found in A, which, because I went to another page, was 17.8 radians per second squared? Well, what I can say is, I already said this has to be torque. And I can say the sum of torques equals I alpha, where each torque is all F sine theta. This was 4 points for each of them. Now, there's only one torque here, and it's at 90 degrees. So there's only one torque. That means the only torque is all F, because it's sine theta. And since the only torque, that means that all F equals I alpha. So all F equals I alpha. And if I want the force, I just divide both sides by O and say the force equals I alpha over the radius. Now, as for I say to treat it like the sword around the end as 1/6 ml squared. Side note, that was fun to calculate because it's not really around the end. It's not. I did a bunch of math to get there, and then it came out to be like 1.578 or something. I'm like, close enough, 6. And so I would say the moment of inertia is 1/6 ml squared alpha over O. I think I actually solved for I separately. No, I didn't. Which is the same as ml squared alpha over 6O. And so it'll be, M was written on the previous page. I lost it. 47 kilograms times L, also on the previous page, 1.86 meters, times alpha over 6 times 0.045 meters. And you get 10,700 meters. This does seem pretty big, but if I do use phrases like what ridiculously large force, it's probably going to be pretty big. And that covers torques. I didn't cover energy last time. As I said, I don't always. Energy normally shows up in the first problem and sometimes shows up in 3 or 4, but I wouldn't guarantee it. I will guarantee, though, that the rest of these boxes will be hit. There will be angular momentum. There will be torque. There will be centripetal acceleration. There will be kinematics. There will be the relationship between linear and rotational. Although that one can also show up in question 1 if I do rolling. Which now I'm kind of trying to remember what the problems are and to see how they show up. But I don't, because I literally don't remember. Any questions though? As I move slightly off camera because now I'm all like, since I messed up last semester, what guarantee is though that I didn't mess up this semester? So I'm going to move off camera and delay as I try to find the exam. Ah, I found the exam. Okay. So those boxes are going to show up. As I said though, energy this one's only a maybe. And when it does show up, it's sometimes in question 1. And this one also sometimes shows up in question 1. But the other 4 would definitely show up in questions 3 and 4. And these other 2 might show up in question 3 or 4, or might show up in question 1. That's the general setup. So I got 9 minutes left. I'm going to do practice problems all day on Wednesday, but I'm willing to do anything now if people want to see it too, if I can do it in 8 minutes. So questions. So anything I can help with. Crickets. Okay. I'm going to assume that means you think you're good. Once again, to class on Wednesday, I will be doing whatever you guys ask. If you know there's something you want me to cover Wednesday, if you shoot an email saying, hey, give me this type of problem, I would be grateful because I'll prepare it ahead of time. Otherwise, I'm going to waste some of class going and digging through problems and trying to find one that matches what you asked me for. But so yeah, if you know what you want to ask, just shoot me an email, say, hey, this type of problem. But other than that, Wednesday will last up to 50 minutes as long as you guys ask me questions. If you don't have questions, I just sit there and say this is a waste of our time. Yeah, have a good day. I'll talk to you then. Bye.